I think times are changing though, especially with COVID, people being able to work remotely and um, I think businesses are going to have to be a little bit nicer to employees moving forward. Okay. So we were going to talk about finite element methods, right? Yeah.
Yep.
I thought I had this organized, and apparently, I got distracted. Okay. Let's What's today? 30th. Have you, before we get started, have you guys heard anything about fall, about classes being in session or remote? What's been communicated to you from the university?
I think they're going to give us the option to choose between like hybrid or fully online or in person.
Yeah, I agree.
Oh, I thought it was in person, but I can't remember why.
Yeah, I haven't heard anything, but I feel like they would have said by now if we were gonna do like online.
I think there was an announcement quite a few months ago that had indicated that it was going to be on campus in person. But I'll let you in a little insight. There was a poll that went out with faculty, and it's like overwhelming, like 70% of the faculty want to stay remote. So I'm curious if they're going to change. I'm curious. I'm really curious about what's going to happen. I wasn't invited to that poll because I'm considered adjunct or part-time faculty. But I'm sure your mind goes to some of the same places my mind goes when you think about the folks that were part of that poll. So I'm curious what's gonna happen.
Well, aren't a lot of the engineering professors? A lot of them are adjuncts, so like the representation probably really wasn't that great.
Yeah, there are a lot of adjunct, but I mean the core people that own the classes, are there. So yeah, I don't know. I was just curious if you heard anything, because I think I get all of the student notifications, but sometimes I don't pay attention to them. So I didn't know if you had heard anything else, but it's going to be interesting. Okay. So finite element methods. So this is kind of a cheesy little overview. I don't think I've given this to you before, so if I have, I apologize. I don't think we got to this. So computational methods. to solve boundary value problems. So this is just kind of generic. We're not talking about finite element methods yet. Boundary value problems, BVP. There are finite difference schemes. There's the finite element method. Sometimes referred to FEM or FE. There's the finite volume methods. And there's a boundary element method. We are only going to be talking about finite. I guess sometimes the finite element method, you'll see it abbreviated as FA, finite element analysis. People will refer to it kind of incorrectly. Usually the business majors or the people that did, pottery will use that terminology. Because really this means failure analysis, right? From an engineering perspective. But if you're reading a paper and you see that, you have to look at the context and see what they really mean. And kind of a general overview of mathematical models. Is in this column, we're going to make a little table. Physical phenomena. We're going to call this field variables. And governing equations. So the one that we're interested in is the first one, and it's the deformation of solids. And our field variables are displacement as the function of x. So as you go through something, so this could be, because u is a vector, this could be x, y, z So X is referred to more as maybe a better way of writing this would be like UI and then some other variable ij. So it's anywhere within in the solid, displacement anywhere with the solid. So it's displacement, it's strain, and it's stress. And if we have a nabla dotted with stress plus B. So remember we wrote out this once before. What was nabla? It was remember it was just a tensor. It was the partial derivative field. So that's the partial derivative dotted with a stress tensor plus a body force has to equal 0. In this domain, this is omega in omega. So omega is just a domain. And this is referred to in this perspective, a balance of linear momentum. And for balance of angular momentum, you have to have your stress tensor has to equal the transpose of your stress tensor. So it has to be essentially symmetric. So this is balance of angular momentum. Now, for this to happen, if we have for this stress tensor to equal the transpose of the stress tensor, that means that our stress tensor is symmetric. What does that tell us about the strain field? Wouldn't it be symmetric also? Assuming that we're not talking about plane strain versus plane stress, just you have some generic volume. And we have our essentially our constitutive equations. So we have, you know, stress is equal to our elastic modulus times our strain. So for this to be true, that means the strain is the same, but what does it tell us about our material? What does it tell us about the stiffness of our material? It's essentially an isotropic, right? Because our stiffness matrix is symmetric also, which means we pretty much have an isotropic material. So what this, in very subtle terms, is telling us is that we're dealing with linear elasticity and isotropic materials. Okay, so that's the first one. And then we have fluid flow. And this one uses a U as well, but in this particular case, it's velocity. And then P, pressure. You know what? I forgot something. Sorry. I'm going to erase this and move it down. I forgot something for the above that I wanted to. I misread my notes here. I had a couple other things to add. So it's a different form than you've seen before. So what we just described, I'll write it out. We said stress is equal to C E. So this is linear elastic, constitutive law. So to be very black and white about it. But the kinematics looks like this. Strain is equal to 1/2 nabla U plus nabla U transpose. Remember, these are just partial derivatives. So I think you haven't seen it in this form before, but this is called the kinematics. For small small displacements. Okay. So fluid flow, I'll just move it down. We're not using. So pressure, velocity, I'm not going to write out the equations for this because it's not so important, but there's two things. We have to have balance of linear momentum and we have to have balance of mass. This is sometimes referred to as continuity. I haven't studied this with regards to finite difference or anything, so it's just a concept. And then we have heat conduction. And we have temperature and flux. And here we have balance of energy. And that looks like nabla dotted with your flux is equal to a forcing function. And you have Fourier's law. Where your flux is equal to minus alpha nabla T. Oh, T is not a vector. Okay, so these are just a couple of examples. Different physical, mathematical models or physical phenomena, field variables, and things like that. So the first thing we're gonna get going with is we're gonna just very quickly look at what the finite difference is. In 1D. So most of the stuff that we're going to talk about, well, all the stuff we're going to talk about with finite element methods, we're going to talk about in 1D, because as soon as you start getting multi-dimension, it gets pretty crazy. But in general, the finite difference is using a Taylor series expansion. So we're going to write out the problem. And we're going to say that we have minus dtu dx. So this is the second derivative of our displacement is equal to f of x in some domain omega from 0 to 1. So we have a domain, one-dimensional. So we say x is equal to 0, x is equal to 1, and okay. So we have this, our fundamental equation here. So it's this plus boundary conditions, BC. And our boundary conditions is we're going to set these and say that the displacement at 0 is equal to 0. And the displacement at 1 is equal to 1. And I'm going to differentiate this and say it's 1 bar. And we're going to say that this is 1 bar here. And we're going to let f exactly equal 0. And we're going to say that 1 or 1 star boundary value problem. So we're going to let f exactly equal 0 for 1 or 1 star with our boundary value problem. We're going to say this is on our strong form. So this isn't going to mean much yet, but when we start getting little bit further, we're going to talk about strong form and weak form.
Sorry, real quick. It's one-dimensional, and you have an x equals 0, x equals 1, but then it looks like your deformation's going in up in a y-axis. I'm just kind of confused what's going on there.
No, it's probably not a good way of writing it. I'm trying to say that, yeah, so your displacement can come off of this line. So it kind of is two-dimensional, but our x is it's a single axis. So yeah, our u could be vertical in this particular case. So yeah, it's coming off of that line. And it's supposed to be very conceptual. So it's a 1D, x-axis, but we can have a displacement in 2 dimensions. So, well, that's probably not a good way
The
of
part
writing
is
it.
one-dimensional. The part is one-dimensional.
The part is one-dimensional, but we can have displacements going vertically.
Okay, yeah, okay, that makes sense.
Okay, yeah. So we're going to evaluate the displacement of our one-dimensional part at x equals 0 and x equals 1, but we can have a displacement, either way. So our u at 0, our u here is 0. It's not up or down. And then our u at 1, we're saying is one bar, which is up. So our domain, yeah, and our domain 0 to 1. So that's right. So we're going to call this one, actually. So it's this one here. They're one and the same. And now we're going to write out what our 1 star is. 1 star is minus u double prime. And you can see that this is the same term as this right here, right? It's a second derivative of u. So we're going to say that this is equal to 0 in a domain equal to from 0 to 1. And we're going to say that u at 0 is equal to 0, and u at 1 is equal to 1 bar. So it's literally identical, right? There's nothing different between 1 and 1 star, other than I have in 1, I set u double prime equal to f of x. And in 1 star, we've set it equal to 0. And so this implies u of x is equal to x. So what we've created here with this 1 star is kind of an alternative reality, or an alternative domain, if you will, because we're forcing that u double prime to be equal to 0. In our real problem, our number 1, it's not. It's equal to this f of x that we don't know what it is. So we're just going to assume it's 0. So we're playing the mathematical game that we're assuming it's equal to 0. But technically it's different, right? So then we look at the Taylor series expansion. And we need to do it for so we'll do it. Why do I have this written out twice? Oh, that's why. Okay. So we have 1. So we have our displacement times x plus the change in x is equal to displacement of x plus the first derivative x times change in x. It's not many, it's change in. Plus u double prime of x change x squared over 2 plus, does this look familiar to any of you? That took, was this in 201 or 202? 202? No? You guys didn't do Taylor series?
I think we briefly used the first 2 terms in Taylor series for something in 20.
Yeah, we're getting we're getting to that. Plus higher order terms. Plus higher order terms. So person I took this from called it hot. And now now applied to the problem. So that was a kind of a general one. And it looks the same except for we subtract the delta x at the beginning. So I have a subtraction here versus an addition. Delta x is equal to u of x minus u prime of x delta x plus u double prime delta x squared over 2 minus, so we alternate the signs. Delta x 3 over 6 plus 1, 2, 3, 4 x delta x 4 plus higher order terms. And then you add 1 and 2. So you get u of x plus delta x plus u x minus delta x minus 2u x is equal to u, that's double prime x delta x squared plus u 1, 2, 3 x delta x to the fourth over 12 plus higher order terms. I'm going to divide by the delta x over 2. So u x plus delta x. This looks nasty, but it's nothing compared to the actual the finite element method. Minus 2 u x. Third derivative x delta x squared over 2 plus higher order terms. Where my mouse go? Therefore, second derivative of u, function of x, is approximately u x plus the change in x plus u x minus the change in x minus 2 u of x over delta x squared. Or, and I'll call this 3. I have this numbered. Yeah, I do. We're going to call this minus u double prime of x is equal to 2u of x minus u x plus delta x minus u x minus delta x over delta x squared. So this second derivative of displacement, this minus u double prime, is this guy, right? That same thing. We've come up with an equation for it based on boundaries that we were giving using Taylor series, and we drop off the higher order terms. The higher order terms are meaningless. They end up being, like nothing. So we drop those off. And I think, Jacob, you had mentioned you use the first 2 terms and something that you've done early on. And that's
I seem to remember that. Yeah.
Yeah, that's typically what you do. It's you end up dropping off everything. I mean, it's specific to your problem, but you end up using, like this. Because these values, out here end up being very insignificant compared to the rest of your problem. Like machine precision, like tiny, like especially when we're talking about displacements, they're so small that are really, really meaningless. It's your u of x is the big one. It's this guy right here. This is your big one, the big contributing one, and then the derivative adds a little bit, but that's the big one. So you're using the derivative term, I guess, in an effort to be conservative and say, yeah, I looked at the next decimal point. Okay, so what we have here is we have this line, right? I said we're going from x equals 0 to x equals 1. And these basically these spots here, we can call these nodes, if you will. And you could imagine that this could get broken up into a whole bunch of them, right? So we could have, you know, all kinds of ones that we discretize this and break it up into. And when we're talking about the change in X, we're talking about between nodes. And if we define it with two nodes, X equals 0 and X equals 1, we're talking about, you know, it's that change. But it could be something very small. And you can go from a situation where you're indexing these, right? So if we refer to these as like an I, maybe this one here is I, and this one here is I plus 1, and this one is I plus 2, I plus 3. So you increment on, you can add those. So you get this X I plus 1 essentially is your routine kind of going through here, is equal to X of I plus the change in X. And let's let U X sub I equal U sub I. So we're just making this up, right? So we're saying we're going to have these incremental little changes, I'm calling them delta X in our Taylor series. And yeah, those are actually displacements, right? And so that's how we're going to call those. And then we're going to approximate minus U double prime of X at X equal to X2, X3, Xn minus 1. There's no need to estimate boundaries because they are known. And that was U1 is equal to U X1 is equal to 0. We defined that earlier, right? X equals 0 was U equals 0. And U Xn, so all the way at the other end, is equal to U of 1, which was equal to 1 underscore. Now we're going to use equation 3 to find X of 2. And that's going to be 2U X of 2 minus U X of 2 plus delta X minus U X2 minus delta X This whole thing was divided by delta x squared. And let me fix my brackets here. Are you guys seeing anything here of interest? So what is x2 plus delta x? X3? And what is x2 minus delta x?
X1.
Okay. Awesome. You guys aren't sleeping. So we have 2 u of 2, so the displacement at our 2 node, minus the displacement at our 3 node, minus the displacement at our 1 node, divided by the change in x squared. And then you repeat for x3, x4, x4, 2xn, and discretizing
xn or xn minus 1?
xn minus 1, thank you. Discretizing minus u double prime x equals to 0 leads to u1 equals to 0, which nothing new there, right? That was a boundary condition. Minus u2 double prime. Oops. We'll just call this u double prime x2 is equal to 0 minus u double prime x third is equal to 0. And we'll keep going on with that until we have a minus u double prime xn minus 1 Jacob equals to 0. And we'll get a u of n equal to 1. And this will lead to a u1 equals to 0 to u2 minus u1 minus u3 equals to 0 to u3 minus u2 minus u4 is equal to 0 to the un equals to 1. And that gives you this, basically this, you end up with this matrix of 1, 0, 0, 0, minus 1, 2, 1, 0, 0. So you get this huge matrix multiplied with your displacement vector, u1, u2, to un minus 1. And that is going to equal this 0, 0, 0 down to 1. And in general, what this gives you is you can say that this is K. This is D. And this is F. Does this look familiar?
Hooke's law.
It's Hooke's law. And those of you that have played around with finite elements a little bit you should know what or at least have heard what a K matrix is. A K matrix is a stiffness matrix. So stiffness matrix, your stiffness times your displacement is equal to your force. It's really kind of the same thing as writing, I mean, it's a little bit different, but same phenomena, right? Stiffness, displacement, and force over area. It's the same fundamental principles or your constitutive laws. That's your K matrix. K, your stiffness times your displacement field is going to give you your force field. We're not done yet. So now 5. I won't put that yet. Now we look at a variational principle. And does anyone know what that means? So this is a solution right here. So what we did here, I don't want to draw a hard line here, but I'm going to kind of put a dotted line. You have this finite element, or you have this elasticity problem, right? We're looking at the second derivative of our displacement field is equal to a force in this domain 0 to 1. And we have a boundary condition where it's fixed at one end, and we're saying it's just 1 bar at the other end, some imaginary number. And we use Taylor series expansion to see what that looks like, to understand what those displacements look like. And that leads to, this matrix here where we have the K matrix times our displacement field is equal to our force. And that, excuse me, that could be a solution all on its own. You could be done at that point if that's what you're looking for. But it has some error associated with it because of leaving off all those higher order terms. So if you wanted to dig into it a little bit deeper, you can do that and use these variational principles. And that's where you take this problem and you minimize it. So you're looking at, you guys remember minimizing functions? So we're looking at a variational principle. So it's kind of like the next step, like you want to get a little bit better answer rather than taking all of those higher order terms of Taylor series. You would look at the same problem from a variational perspective. So I'm going to call this 5 because you really would start off with the Taylor series and go through that process before doing this, but you could jump to this if you really wanted to. So 5, we're going to say is minus u double prime is equal to f in omega is equal to, and we're going to call it different, a to b. So that way the problem's a little bit different. And we're going to say that our displacement is our displacement a is equal to 0, and our displacement at b is equal to 0, and our domain's a little bit different in this particular case, because we're going to say that it is like this funky shape. So x equals a, x equals b, and we're going to call this line displacement star of x. Okay, so this is 5. This is a boundary value problem that we have written here. And really this f should be an f of x, right? Because it's it may not be consistent. And then our problem statement is let u star of x be the exact solution. And let's let u of x be a numerical solution. And so we're going to define this variational. And we're going to call this I of u is equal to 1/2 the integral of a to b u prime minus u star squared dx. And that's equal to something like 1/2 the integral of a to b u prime squared plus u star prime squared minus 2u prime star prime x equal to 1/2 the integral of a to b u prime squared dx plus 1/2 the integral of a to b u star prime squared dx minus the integral of a to b u prime u star prime dx. Now we have u prime u star prime is equal to u prime double prime plus u star prime. Therefore, our I of u equal to 1/2 and integral of a to b u prime squared dx plus 1/2 integral a to b u star prime squared dx minus the integral of a to b u star prime minus u star double prime dx and write it again, minus 1/2 a to b u prime squared dx. Do I have to write all this? Yeah, I will. Plus 1/2 integral a to b u star prime squared dx minus u star prime. This term is going to go to 0. A to b plus the integral of a to b u star double prime dx, and this u star double prime is equal to minus f, and we know that because that was a problem statement, right? We know that because of here. We also require u of a equal to u of b equal to 0. So we get this variational is equal to 1/2 integral of a to b of u prime squared dx minus the integral from a to b of f. Yeah, should have used different notation here. Fu dx. And what's interesting is this here is stored energy. And this, does anyone know what this one is? External work. And we want to minimize U. So if we remember, we have U A is equal to 0, U of B equal to 0, and U is continuous. So the variation U star is less than or equal to the variation of U. I know that doesn't mean much for you yet, but let me write this in a different way. Spring analogy. So the variation of x is equal to 1/2 kx squared minus f of x. Does that feel a little bit more comfortable seeing it that way? So 1/2 your spring constants times your displacement squared minus your force times your x. And you minimize that. So you do d, take the derivative of that with respect to x is equal to 0, right? That's what we're doing. We say to minimize this. So we're saying that our kx minus f is equal to 0. And that gives us f is equal to kx. So our variation of u is the punchline. What is it? Does anyone know? Potential energy functional. That's supposed to be mind-blowing. It's not, huh? No. Bummer. What does this all mean? Think about the elasticity problems. What was the boundary value problem that I set up for that we looked at, towards before the break, before we did plane strain and plane stress. Remember what the boundary value problem was that we were trying to solve, or that we were going to solve? Nothing?
Was it the string problem?
No,
Was it
just
the string?
just in general, the problem that we're trying to solve, our boundary value problem, where we have a well, let me just write it. Gotta look it up here. We essentially have the integral of a traction dA plus the integral of our body force dV is equal to 0. And then we use divergence theorem and we ended up with this partial of Tij respect to xj plus rho bi is equal to 0. So we have a body for, we have a elasticity force and we have a body force. Isn't it really just kind of the same forms of all the stuff that we're looking at here? Kind of like this right here, stored energy, external work. You kind of see that same form here? Can you kind of envision, so what goes into this Tij? Tij is stress, right? That's a stress tensor. And stress is based on what? Stiffness and displacement. So can you see that that is stored energy? Right? You take a beam and you bend it, and that energy is stored in there. And if we minimize this function, like if we were to say something, like don't write this down because this is totally wrong. I'm just trying to make a point here. If we were to do something like this and we were to minimize it, that's going to go to 0, which means this guy is the potential energy functional if you minimize it. That's kind of cool, isn't it? I think so. You take a body, you deform it by a force, and it has all this stored potential energy. That's pretty cool. I mean, we know that from a spring, but think of it as our continuum potato. So what I wrote here is totally bogus, but conceptually it's right. So I got to put an X through it. So you guys don't go design O-rings in the wrong unit system or something. Okay. You guys are quiet. Is it because you're disappointed that you don't have Wednesday off? Or you don't have Thursday off? No, nothing. You guys are just done for the day. No. All right. Well, I hope you have a good evening, and you're not too disappointed about not having Thursday off, so we can continue our talks. I'm excited because I have my meeting here in a couple of minutes. So I officially got promoted on Friday. So Jacob.
Oh.
And so now it happened late Friday night. And so now I have the luxury of going to 8:30 meetings on Tuesday night.
Congratulations.
So yeah,
congratulations.
fun for all of us, I guess. So, all right, folks. Well, have a good night.